All right, let's jump right into it. Today, we're unpacking a massive paradigm shift in how we handle hardware intent and verification. If you're an engineer, you already know the ultimate wall we hit, proving that the circuit you designed actually behaves the way you intended on silicon. It's incredibly tough. But today, we're looking at a way to completely tear down that wall. We're going to logically dissect the complete architecture of what we call Layer 4 verification evidence, a totally new structure specifically designed for human-AI collaborative development. So let's dive in.
Okay, let's look at this quote right here. Intent is hard to say and easy to mishear, so stop saying it. Man, that is such a powerful statement, isn't it? In our day-to-day development, pros, just using words to explain things, literally deceives us. I mean, think about it. A single interpretation of a clock edge can completely trip up even the person who wrote the specification. That's exactly why we have to stop relying on words and start leaning entirely on machine-checkable evidence.
So, here's our blueprint for today. We'll look at the evidence layer for intent, explore why a simple folder doesn't cut it, and uncover the sheer power of the conformance matrix. Then, we'll go through the 3 disciplines for turning waveforms into evidence, the human-AI division of labor, and finally wrap up with a specification that utilizes 4 verbs.
Starting with Section 1, the evidence layer for intent. You know, getting an AI to write Verilog code, honestly, that's pretty much a solved problem at this point. The actual bottleneck, the real challenge we face, is figuring out how to convey true hardware intent to that AI.
When you try to communicate, hey, it needs to behave exactly like this, clock by clock, on real silicon, traditional prose just falls flat. An AI coder can't reliably consume written words and translate them into flawless action without misunderstandings. Words are just messy. And that is exactly where Layer 4 steps in. Layer 4 is this entirely new apparatus that captures real silicon behavior and communicates it as undeniable, machine-checkable evidence. We're talking hard proof here, not just talk.
Moving to Section 2, why not just a folder? Now, you might be wondering, why didn't the architect just drop a test folder into the project directory and call it a day? Why go through the trouble of building out an entirely separate, formal layer? This is really the core of the paradigm shift.
Well, verification has to be a fully recognized sibling layer, because these 4 layers answer fundamentally different questions. Layer 1 tells us what it is, that's the normative rule. Layer 2 is the intellectual provenance, basically why it was decided. Layer 3 gives us an illustration, a provisional way to actually build it. But Layer 4? Layer 4 is the empirical provenance. It is the definitive proof that the build behaves exactly as specified. A simple testing folder just can't carry that kind of architectural weight.
And this brilliantly illustrates the dynamic between them. Layer 2, our record of decisions, and Layer 4, our record of behavior, actually form a continuous conversational loop. The reasoning layer, Layer 2, asks questions by handing off resumption hooks or unresolved queries. Then, the evidence layer, Layer 4, answers back with a hard verdict, backed by empirical data. The reasoning layer asks, the evidence layer answers. You absolutely need independent layers to support that kind of robust, ongoing dialogue.
All right, Section 3, the conformance matrix. Let's look at how this actually plays out in practice. This single file acts as the front door to Layer 4, and let me tell you, it basically weaponizes transparency.
The real superpower of this matrix isn't just that it tracks what is verified, it's that it makes what is unverified literally impossible to hide. It forces that slightly uncomfortable truth out into the open. As engineers, we can't just hide behind a blanket statement like, oh yeah, all the tests passed, when there are still gaping holes in the verification.
Just take a look at how Layer 1 predictions map onto actual verification statuses here. Mature features, like the memory timing contract, proudly show up as passed on silicon, but newer mechanisms, things like the program enqueued band or external stack nesting, the matrix relentlessly flags those as untested. It completely refuses to let the illusion of all tests passed cover up the reality of untouched features. And if there's a known discrepancy, it's clearly marked as an anomaly. There's absolutely no sweeping things under the rug here. On to Section 4, 3 disciplines for turning waveforms into evidence. Because Layer 4 isn't just some abstract high-level concept, it's a highly operational set of structured habits you apply every single day. So, there are 3 absolute rules you've got to follow. First, you state your expected outcomes before you make any observations. Second, every waveform requires a concrete verdict. Seriously, a folder stuffed with unannotated waveforms isn't a proof, it's just a maze. And third, for things you can reproduce, like in ModelSim, you keep the execution recipe. But for non-reproducible things, like a fleeting moment caught on signal tap from a physical board, you keep the actual evidence, the raw VCD data itself, as your proof.
That first discipline is absolutely crucial. Imagine you're working with a prescaler phase probe. Before you even touch the bench instruments, you have to write down your prediction. You state the ideal, say 25 clocks, and any suspected anomalies, like a 1 to 4 clock jitter. You're setting the pass and fail criteria up front. There's a massive difference between just stumbling upon something on the bench and actually proving you understand the silicon by testing a preconceived hypothesis against it. That is how you prove intent.
Which brings us perfectly to Section 5, the perfect human AI division of labor. This right here is the operational core of how Layer 4 functions in the real world.
So the crucial point here is the explicit division of labor. Neither the human nor the AI could possibly run this verification loop on their own. As humans, we operate the physical instruments, things the AI can't touch, like Quartus, JTAG, and Signal Tap. In return, the AI takes on the heavy intellectual lifting, authoring the test stimuli, drafting expected behaviors, analyzing the waveforms we feed back to it, and even diagnosing faults. We observe the physical world, and the AI analyzes the data. This systematic, evidence-based dialogue is the absolute heart of Layer 4.
Finally, let's wrap up with Section 6, a specification with 4 verbs. We are closing the philosophical circle that this whole project has been drawing from day one.
The core thesis all along was that a spec should be written so an AI can read and execute it. We've seen in past logs that AI can understand, it can reason, and it can implement. But there was always a fourth unspoken verb, verify. And not just verify in a cozy, closed simulation, but verify against real, unforgiving silicon. Layer 4 officially establishes that fourth verb.
This completely changes how we view our code. Think about the example programs in Layer 3. They're really just pedagogy, right? They show how to use something, which is why they are clearly marked as provisional. But a Layer 4 conformance program, that is hard evidence proving the stimulus actually works. A program only gets promoted to a Layer 3 example once it has been battle-tested and refined by the undeniable evidence produced in Layer 4.
So I want to leave you with this final provocative thought. Is your project specification actually verified on real silicon? It is time we stop relying on easily misunderstood spoken intent. In this new era of human-AI collaboration, we need to start demanding machine-checkable proof from each other. That is exactly what this Layer 4 architecture empowers us to do. I highly encourage you to apply this paradigm shift to your own projects. It's a real game changer. Thanks for joining me on this deep dive.